Okay, so we have a problem that a student shared with me, where an amusement park ride consists of a car moving in a vertical circle, with a rigid boom line of negligible mass. Okay, we know that the combined weight of the car and riders. We know the circle radius of the circle, and at the top of the circle, we're asked to find the force of the boom to keep the thing up and rotating at that particular speed. We're given the speed as well. So the math for this problem is not particularly complicated. We just set up Newton's second law in the vertical direction, and we get that F net is equal to MAC. We're choosing the convention of upwards as positive and downwards as negative. And okay, we just set up the net force. That's just going to be the force of the boom minus Fg is equal to, well, centripetal acceleration is going to be negative because centripetal acceleration is downwards for circular motion at the top, right? So this is going to be a minus mv squared over r. Now, this is fairly straightforward mathematically to just solve. If we know mass, we know v, we know r. Remember, mass can be found from the weight, right? And Fg itself is just the weight. We can solve for Fb pretty easily. But what's a little bit interesting about this problem is you note that as the magnitude of v changes, this entire thing gets more and more and more negative, right? For a very, very, very fast moving circle, we're going to find that this entire thing is very negative, which means that by equality, the left-hand side has also got to be very negative, right? But force of gravity is fixed. The only thing that's allowed to change is the force of the boom. So what this is sort of saying is that for very slow moving Ferris wheels, the force of the boom is going to be in the upwards direction. But for very, very, very fast moving Ferris wheels, what this means is that force boom actually has got to change direction. It's actually got to start pointing downwards. It's kind of odd, right? It's kind of an interesting effect. And well, it's, how do you put it? It's kind of intuitive, right? Because you can imagine that as this thing starts rotating around faster and faster and faster, what this essentially is saying is that this rod has got to be doing a lot of let's call it heavy lifting in order to get this thing, incredibly fast moving thing, to be changing direction. And the faster it's moving, the more it's got to be pulling it backwards to rein in its velocity and get it to change direction. So, from a physical intuition perspective, I think this kind of makes sense. Like, if you've ever just sort of as a child swung a bucket around, you notice that right, if you're a child swinging a bucket around, what you notice is that the faster you swing the bucket around, the more it tugs on the rope, right? And this is the exact same effect. Yeah. All right. Okay, I think that settles it.